till now what we were looking at was on policy learning, where the task was that you have a reward function and you want to generate outputs that have high reward. Now we'll go to a slightly different route. Instead of saying that I want to maximize the reward, I want to generate outputs that maximize the reward, we will say that I want to given a preferred and a rejected pair, I want a policy that generates the preferred pair with higher probability than the rejected pair. So we are going to do contrastive learning, and I don't know if you guys are familiar with contrastive learning. Generally, contrastive learning is we use, let's say, when we are doing metric learning, or we are trying to learn a similarity function. We say that okay, this particular example should be more similar to A and less similar to B. And here the idea is going to be very similar, that we have a preferred pair and a preferred response and a rejected response. And what we'll say is that the model's output increase the probability of the preferred response while simultaneously decreasing the probability of the rejected response. Okay. And we will study one specific contrastive learning framework, which is DPO, and we will derive it from the PPO or the policy, the on policy objective that we have, on policy RL objective. We'll start with that objective and somehow we will derive DPO objective from there. Okay, so how does PPO, GRPO, and all the other algorithms that we saw so far proceeded? You collect preferences, then you'd first train a reward model using those preferences, and once you have a reward model, you use that reward model to train your policy. So there is a reward model learning framework, and then there is a policy training framework, right? Now ultimately preferences are not getting used here, right? The policy learning framework is using the preferences indirectly, right? Indirectly uses preferences. So the question asked by the authors of the DPO paper is that, do we need this intermediate step of learning a reward model from the preferences, or can we remove this this learning a reward model step altogether? And that's what we will try to do. We'll try to remove this reward model learning step and directly train the policy on top of the preferences. So firstly, why do we need to do that? Like, why do we even care about this? We have seen the pipeline, right? Pipeline is the pipeline for doing PPO. It's a pretty complex pipeline. We have to cover actor critic function. We have to talk about importance weights. We have to batch convert the rollouts into mini batches, then use importance weights, clipping, lots of different tricks to make these online algorithms work. So these are expensive. These rollouts are pretty expensive, and having an intermediate reward model, because the reward model is trained on some small subset of data that we collected, it's not a perfect reward model, and it has its own bias. So if we are adding bias during the reward model training step, and then when we use the reward model to train the policy, we are adding another bias. So at least let's get rid of one bias, which is the reward model training step. So this is the pipeline, the online on policy RL pipeline that we have. We have prompts. These are the prompts, and for each prompt we have a preferred response and a rejected response. This is the data that we have collected, right? And if you are doing policy learning if you are doing on policy learning, what you will do is you will first train a reward model on top of these pairs, preferred rejected pairs, right? And then you will use PPO or GRPO to get your final policy. But if you don't want the intermediate reward model, what you want is that given the preferred and rejected pairs, somehow you should directly learn the LLM policy. This is what we want. And this is what is achieved by the DPO framework. Okay, so what are the desirable characteristics of such a model that we want? What do we, let's say we get a policy pi theta, somehow using which directly learns from preferences. What do we want? What is the desirable thing? Yeah, the preferred response should have higher probability than the rejected response, right? And it should also incorporate this KL term somehow, right? We'll see how DPO incorporates the KL term, but there are other ways to do that. So we want a policy which gives higher probability to the preferred response, but somehow also incorporates the KL term. Why do we need the KL term? Because we don't want to deviate too much from the reference policy. Okay. So let's derive. So now we'll start the derivation part. We will ignore the theta and phi for now. So we'll work in a scenario. We'll assume that pi can be optimized arbitrarily, and the policy can be optimized arbitrarily. We can reach the global optima somehow, and the reward function also can be optimized arbitrarily. We can reach the global optima for the reward function also. And so R star is the so this is the reward model training objective, right? Log sigmoid of positive response. The reward of this is the reward of positive response, and this is the reward of negative response. So the optimal policy is the one which maximizes the difference between the positive preferred output and the reward of the negative rejected output. And what is the so this is the optimal reward. And the optimal policy pi star can be written as a function of the optimal reward function, right? So this optimal policy is the one which maximizes this thing, the expected reward. This is the expected reward, and this is the KL term with respect to the reference policy. So the optimal policy is that maximize the expected reward as measured by the optimum reward model, and while simultaneously keeping the KL term low. So now we want to cut out this reward model training step, and the way we will do is we'll use this equation to express the reward model as a function of the optimal policy. So the optimal reward R star, we'll express it as a function of pi star, and then we'll plug it back in the first equation. Okay, so there are two steps. One, we express R star as a function of pi star, and then plugging it in the reward model training equation, and that will give us a pi star training objective. This will convert this into a pi star training objective, this equation, this first equation. Okay, so as I said, we'll convert, we will use the policy training objective to represent R star, the optimum reward model, as a function of the optimum policy. And how do we do that? We'll derive a Lagrangian for this policy objective. Why Lagrangian? Because we have a constraint. This is a probability distribution. It has to sum up to 1. Pi star still has to sum up to 1. So there is a constraint. So we'll write the Lagrangian. We'll set its partial derivative with respect to the pi star equal to 0. And then whatever we get, we'll plug it back into the reward model training objective. And then that will give us the DPO training objective. Okay, so first step, so this is the pi star training objective. We want a policy such that the outputs sampled from the policy have high expected reward, and the policy should not be very far from the reference policy, subject to the condition that this pi star is the probability distribution sums up to 1. So what is the Lagrangian? Let's write it. L pi, and let's add the Lagrangian parameter lambda. This can be written as the above equation minus beta times KL plus lambda times the constraint. Okay, this is the Lagrangian, and now we'll compute its partial derivative with respect to pi. So what is its partial derivative with respect to pi? Let's first write that let's first expand the expectation, replace the expectation by a summation. So the expectation pi y given x can be written as summation over y belonging to the set of all possible responses pi y given x into r star x comma y. Is this fine? Next, writing the expectation as a summation. The second KL term also can be written as a summation. Any idea how what will it look like? Beta times summation over responses pi y given x log probability and the final term is the Lagrange, the constraint that we had, or that it should sum up to 1. So this is L, this is simply L pi comma lambda. Okay. Okay. Is this fine? I hope this looks fine. Is this fine, everybody? Okay. And now let's compute its partial derivative with respect to pi y given x. So we'll have to do it for each pi y and x combination, and let's assume x is fixed. So for each response, the reason so that you can think that each pi y1 x pi y, all the possible outputs are represent one of the parameters. So each of pi y given x is one parameter. So one should differentiate with respect to pi y given x for a specific y. What do you get? Del L over del pi y given x for a specific y. Let's say generally you think of it as pi y equal to y naught given x. So this will give you pi, sorry, give you r star x comma y minus beta, and not the derivative of this quantity for particular y. This will look like, I'm writing it here, but you guys can derive it once. Pi y given x or pi ref y given x, and for this will be simply lambda, and this we are equating it to 0. So this gives us the optimum reward. And okay, so when we are equating it to 0, this is pi star, right? We are the pi for the value of pi star we are equating it to 0. So r star, the optimum reward, can be written as beta times 1 plus log of y given x minus lambda, or let me write it as beta log pi star over pi ref plus beta minus lambda. So this is some constant that is there, right? So the optimum reward is log probability ratio of pi star and pi ref times beta plus some constant. Okay, and so the this is the expression that we will put back into the reward model training objective. Okay, and before we do that, we are going to do a side track. Just for our sake, we want here we have derived the optimum reward as a function of the optimum policy. But what is the optimum policy as a function of the optimum reward? You can just rearrange the terms and that you will get that. So we'll just sidetrack and derive that also, just for the sake of completion. But this is the equation that we need. Ultimately, the equation that we need is this. This is the one that will plug it into a reward model training objective. So this is the optimum reward in terms of optimum policy. What will be the optimum policy in terms of optimum reward? Just put the terms here and there, and that will tell you. So let's rearrange the terms. R star x comma y minus beta minus lambda equal to beta times log of pi star y given x and let's divide by beta. So r star x comma y by beta minus this beta minus lambda by beta is equal to log of pi star over pi ref and exponentiate both the sides. You'll get e to the power r star x comma y by beta times e to the power minus beta minus lambda by beta equal to pi star by pi ref and now let's write pi star in terms of all the everything else. What we get is pi star is equal to pi ref exponentiated of r star times this quantity e to the power. So I will just call this as c. This particular quantity I will call it as capital C. And since pi star is a probability distribution, this c will come out to be the normalization constant for this this quantity. So c is just a normalization constant. Okay. So the optimum policy that you get when you do, let's say, PPO or whatever policy gradient algorithm, is the reference policy, the policy that you start with, times some function of reward, which makes sense. So we are saying, what does it mean actually? What does this mean? That your optimum policy will give high probability to something only if either of the condition hold. It should have high probability under the reference policy. Actually, both of the conditions should hold. It should have high probability under the reference policy. That means your base model should think that output is already correct. Only then the optimum policy will give high probability to that. And the second thing is that its reward should be high, right? And that's what we started with, right? We said that its KL divergence should be low and the reward should be high for the policy. And that's what this equation shows, that the optimum policy will give high probability only if it has high reward, and also it is desirable under the reference policy. It has high probability under the reference policy. Okay, so actually I kept two slides. I was wondering if I will complete in one slide, so we'll leave this slide alone. Okay, so let's write the two equations that we have. What are the two equations? Pi star for a given output is proportional to, I will write proportional to because I'm ignoring the normalization constant, pi ref times some function of the reward. This is the pi star. And we also had another equation. Does anybody remember what was the other equation that we had? What is r star x comma y? Is beta times log probability ratio of pi star pi ref plus something else. What was it? I don't remember. It was beta minus lambda. Okay, and this is the equation that will plug it in the reward model training objective. Okay, yeah, we will do that. But this is what is saying, that the optimal reward can be expressed as a function of the optimal policy, or in other words, the optimal policy can be expressed as a function of the optimal reward. So then the DPO objective says that, do we really need to worry about all possible reward models? If we can write the optimal reward in terms of the optimal policy, let's worry about only those reward models that can be written in this particular form. So if R star can be written as function of phi star, let's parameterize reward model like this only. So all our reward models will assume to have this form. Plus some constant. We'll assume that our reward models have this particular form, and then we'll put this equation in the reward model training objective. So this is the motivation to them, the equation that the optimal reward can be written as a function of optimal policy. And then they say that, okay, if the optimum reward can be written like this, I will assume that all my reward models can be written like this. And then you put that equation in the reward model training objective. So yeah, this is exactly saying what I was saying, that the reward function can be written in terms of the policy parameters. Let's assume that, and then train this directly on the preference pairs that you have. Okay. So what does that mean? You compute this reward, this log probability ratio reward for the positive. So if you have a preferred response and you have a rejected response, compute this log probability ratio for the preferred response. This is the log. We'll call this as the implicit reward of the preferred response. So this is also called as implicit reward, because you are computing it using a policy. So compute the implicit reward of the preferred response, compute the implicit reward of the rejected response, and then just apply the reward model training objective that we used in the first RL lecture, if you guys remember. So log sigmoid of reward of positive minus reward of negative. So this is the training objective. So we can take this equation, and plug them here, and that gives us the DPO objective. So let's plug it and see what we get. Actually, it's quite obvious what we get, but just let's do it. So what we'll get is argmax over theta summation over all these preferred and rejected responses that we have in the training data. Actually, there should be a normalization also, 1 over dataset size time log of sigmoid of the implicit reward of the positive, which is beta times log probability ratio. Plus beta times the normalization constant minus beta log probability ratio for the rejected response. Minus beta log normalization constant, and this is common between the preferred and the rejected. So all you get is log sigmoid log probability ratio of the, so this we can write as log probability ratio of the preferred minus log probability ratio of the rejected response. Sigmoid and log. So this is your DPO objective that you optimize. Does that make sense? Till now, till here, this point, any questions? Okay. So if you have to implement it, what you will do is you will take your preferred response pass it through the current policy, pass it through that you're training, and then pass it through the reference policy that you started with, and compute the log probability ratio for the preferred response. Similarly, you will take the rejected response, pass it through both the policies, and compute the this should be minus, my bad. Compute the log probability ratio for the rejected response, and then you will maximize the log sigmoid difference between those implicit rewards. And this is pretty as easy to implement as you would do SFT. The only difference is that there are two networks that you'll have to do a forward pass through, but other than that, it's as easy as SFT. You don't have to worry about gradient explosion, or you don't have to worry about high variance, because you're not sampling anything. The preferences are fixed. There is no variance issue or anything. You can just implement it. The only thing you have to worry about is how to choose this beta quantity, what value of the beta to choose. Okay. So where is the KL divergence term? We saw this equation, but how do we know that pi theta and pi ref will stay close? Because there is no KL divergence term in this objective, right? So where did the KL divergence term disappear? Any idea? What happened to the KL divergence term that we had? We started with the objective that had a KL divergence term, and we ended up with an objective that does not have a KL divergence term or anything that looks like KL. So this ratio actually comes from the KL divergence term, the ratio. So if there was no KL divergence, you would simply have log pi theta, but there is a log pi theta by pi ref. So what that means, what are we exactly saying when we say that the reward is not just your probability under the current policy? The reward is the probability ratio, how much your current policy thinks about this output, upon what your starting point thought about that same point, and that ratio is your reward. So that ratio is what we are trying to improve for the preferred response. And let's assume that your reference policy already gave a very good probability to the sample. Let's say it was around 0.8 in the beginning. Okay. And when you train, let's say so if your reference policy already gave 0.8 and the model increase that probability to 0.9, how much is that ratio? 0.9 by 0.8. So somewhere around, I'm guessing 1.1, right? Now, if the reference model assigned a low probability to the response, 0.1, the model can achieve that same increase by, so just increasing the probability from 0.1 to 1.1. So the ratio from 0, if the model increases the probability from 0.8 to 0.9, and the ratio of the model increases the probability from 0.1 to 0.11 is approximately the same, which is 1.1. So what that means is that if the model does not assign a very high probability to a preferred response, if the reference policy does not assign a very high probability to preferred response, even after you do DPO training, it's not going to assign a very high probability. And there have been a lot of papers which show that the probability, if the reference policy does not assign high probability to a sample, after you do DPO, the probability will still not increase drastically. So in absolute terms, the probability assigned will still be low. Why? And this is how it is keeping the model close to the reference policy. So this is the KL divergence term playing. This is the role that the KL divergence term is playing. It's saying that whatever your starting point was, scale relative to that, not absolutely. You don't absolutely scale in probability, you just scale relative to that. Does that make sense? What is the role of beta? So we said that the only thing in DPO that we have to worry about is beta. There is also learning rate, but which is true anyway. Whenever you are doing training, you have to worry about learning rate and other optimizer hyperparameters. But the special parameter that is added by DPO is the beta parameter. So when we were doing RLHF, the role of beta was simple. That if beta is high, that means I give more weight to the KL. Higher the value of beta, give more weight to KL, so your policy will not deviate from the reference policy. But in the case of DPO, the role is slightly more slightly weirder. So let's see what happens here. So if you look at this equation, what does this equation suggest that beta might be doing? If I increase the value of beta, what do you think will happen here? Any idea? So if I increase the beta of this in this objective while training, the model will say, okay, let me increase this difference even more. It will try to increase this difference. Think of beta like a scaling, right? So it's not doing the same role as it was doing in the case of RLHF, where in RLHF its role was clear. It's trying to prevent the policy from deviating from your reference point. Here, it's actually saying that increase the difference between the two rewards. So it appears that higher the value of beta, the model will attempt to increase the gap between the positive and negative response. It's not true. And there's a reason why it is not true. And we'll look at the curve for this. Let's look at some graph for this. So this graph is basically computes the derivative of your so this function log sigmoid beta x with respect to x. So this is the derivative of log sigmoid beta x with respect to x with respect to so this this is the derivative of log sigmoid beta x with respect to x, and the x-axis is your beta. So what it says is that if your beta increases, the derivative actually increases till certain point. What does that mean? That so x is your think of x that as the implicit reward difference that we care about. So as your beta increases, the model says tries to maximize the difference between this implicit reward even more. As your beta, so if you choose a higher beta, the model says that okay, now maximize this implicit reward difference even more until a point. This is the saturation point, and after this point, if you further increase beta, the model says okay, now let's not increase the implicit reward difference further. Let's start giving lower weight to the implicit reward difference further. So after the saturation point, the gradient for the implicit reward difference actually decreases and policy becomes less contrasting. So the role of beta is not very linear like in the case of RLHF. Here beta can actually increase the difference between the implicit reward or decrease this. So beta has to be chosen quite carefully, and most of this choice is done in a hyperparameter training framework. Although I wonder there might be more, people should come up with more better strategies for choosing beta. But right now the current approach is that the way people do is that they assume beta is your KL strength ratio. Just like in PPO, they assume that beta is your KL strength. Higher the value of beta, the closer the policy will stay with the reference policy. And if you are lower beta, then your policy can deviate faster from the reference policy. And if you are doing DPO training, start with beta somewhere around 0.1, 0.05 or something. And then keep a watch on this KL divergence term and your accuracy term. And if the KL divergence term starts increasing, then you increase the beta. And if your accuracy starts decreasing or accuracy starts saturating, then you can decrease the beta. Okay, so this completes the DPO objectives. We talked about reward hacking when we started policy gradient, and reward hacking generally means that if you have a reward model, the reward model has some bias because it is not perfect. It has some bias. It may assign higher reward to, let's say, outputs that start with a specific token. And if you use that reward model for training, what will happen is that the model may start generating that token repetitively. Or it might be the case that your reward model likes outputs that are longer, more verbose, have a lot of repeat the same thing multiple times. I mean, your reward model can have a lot of different biases. And whenever you try to optimize with that reward model, you will end up with a policy that keeps on repeating. So this is called reward hacking. And each reward model can have its own bias. So what people do is they ensemble a bunch of reward models. Ensemble means that instead of feeding the output to one reward model and getting one number, you will take two reward models, three reward models, and take the average across them. And what the idea is that the more reward models you can average across, the less bias will be present in that average reward. This is just like ensembling that you do in your ensemble methods, reducing the bias effect of bias, the reward model bias, by averaging. Does that make sense? Okay. The other thing you can do is that you put a constraint that the outputs should be diverse, and that will prevent the model from sticking to a specific mode of the reward model distribution. Reward model let's say has a mode on the word the. You say no, the output should be diverse. So the model will be forced to look at other outputs which are not in that mode. So this is the problem of reward hacking in policy gradient. What happens with DPO? In DPO, we don't have a reward model. So does reward hacking still occur? Can still occur? But so we don't have a reward model. What we do have is a preference pair. So what can happen is that if you train using DPO, the preference pairs may be preferred or rejected for some reason. The user may have selected a output over another output for some reason, right? But the reason is not there in the. I mean, there is no way for DPO to understand that reason and use it, right? And we will look at how those reasoning can be used when we talk about reasoning much later in the lectures. But DPO itself does not have any way to use that reasoning information. So what DPO can do is that it can look at those output, can think, oh, maybe this particular sentence has this particular word, or maybe this particular sentence has this particular grammatical structure, and that's why it was preferred. And your policy's probability of that grammatical structure can increase. So this is your so it's not hacking the reward model here, but it's hacking the preference pair, because it does not have complete information about the preference pair. So you can solve it by having a lot more preference pairs where the model learns, okay, that was not the reason, maybe there is some other reason. So it will try to ignore the obvious reasons. So you can add an extra loss, which is the supervised loss, on top of your positive response to deal with this preference hacking problem. Finally, we want to talk about, so there's one more thing we want to talk about, which is that there is a inherent bias in the DPO objective. So let's look at the DPO objective again. It says that increase the implicit reward. This is your implicit reward of the positive response. And this is your implicit reward of the negative response. So given a preference pair, it says increase the implicit reward of positive, decrease the implicit reward of negative. Right? This you want to decrease, and this you want to increase. So now let's assume that you have just started training, and your reference policy assigns the same probability to the preferred and the rejected, and both of them have a probability of 0.5. Okay, and there is some output y naught, which is just a repetition of the word the. This is some output whose probability you have not mentioned in the objective. See, this particular y naught does not occur in this objective at all. But ideally, you don't want its probability to increase, right? So you only care about preferences or outputs that are there in your data. You don't care about outputs, some random outputs, right? But when you do training, so initially, because at the beginning of training, both of them are 0.5 pi ref, and because you're starting training, pi theta and pi ref are same, so they also will be 0.5. Does that make sense? So after a few steps of training, either this ratio will increase, this particular ratio, and this ratio will decrease, right? So let's say this ratio went from 0.5 to 0.6. Sorry, the pi theta went from 0.5 to 0.6, and the pi theta y minus went from 0.5 to 0.1. So I see, ideally what you want is that if the probability of a certain output decreases, all the change in probability should go to the y plus. It should not go to something else. But you're not telling it anywhere in the objective. So this probability can actually go to a sample which was not in the objective at all, right? It can go to certain y naught. So here pi theta of y plus increased from 0.5 to 0.6, and y minus it decreased from 0.5 to 0.1. But now some new outputs appeared whose probability also increased, because you're not telling the model what to do with the other outputs. you're decreasing the probability of y-, but you're not saying where that probability mass should go. And that is a risky part. And this is something that happens if you keep on doing DPO training. You encounter outputs you did not have in the objective whose probability increase suddenly, and they will be meaningless outputs. So this is a very common experience if you do DPO for a long time, and if your policy is not very sharp to begin with. If your starting policy was very sharp, then deviation is a bit difficult. But if your policy was more smoother, like it had high entropy, then it can start deviating if you do DPO. So how do you deal with this? The solution is online DPO. So what is online DPO? It's just like we had PPO and everything. You have a reward model, or you have a LM as a judge. And now instead of using the preference pairs, you will sample the outputs from the policy and ask the judge to create those preference pairs. So you will create the preference pairs in an online fashion. So instead of having a fixed set of preference pairs, you will sample the outputs, create pairs out of them, and get them judged by a reward model or a judge model or whatever, and then use that to do DPO. And then once you have done DPO, you will repeat the cycle. You will now sample again a bunch of outputs, get them labeled by a judge model, and again do DPO. And you will repeat the cycle. So what is the advantage here? Suppose certain output like the or certain weird outputs whose probability you don't want to be high. So suppose that output appears. When you give it to the judge model will immediately say this is a bad output, and so your model will learn to decrease the probability of those outputs. So it's a feedback loop where if any error signal appears in your model, if the model starts making a certain type of error, it will be immediately corrected. So this feedback loop has been shown to improve the performance of DPO by a huge amount. And as you can see here, the online DPO methods actually work much better than the offline DPO methods. You can see the win rate difference between online and offline DPO. So this is where we will end reinforcement learning and alignment lectures. So what we have learned is that DPO can learn the policy directly from human preferences, but there are some issues. It can capture differences which are unimportant because it does not have any way to know what are the important differences. And also it can be biased towards samples that it has not seen during training in its preference pairs. And you can prevent these bias by doing it in DPO in an online fashion, where you sample, get for feedback, train, again sample, get feedback, and train. Okay, and these are some of the resources that, so the first one is the original DPO paper. The second one is a more easy to understand explanation about DPO. The third one is a link, is the online DPO paper. And fourth one is the Hugging Face DPO trainer. And fifth one actually teaches you how to build DPO from scratch. Okay.